Caiazzo, who's a postdoc at Caltech. So she's going to tell us about finding and studying white dwarf merger remnants with ZTF, LRIS, and CHIMERA.
Yes. Thank you, everyone. Yes, I'm going to talk about, yes, thank you. Very strange white dwarfs and how I'm studying them with Palomar and Keck, in particular ZTF, LRIS, and CHIMERA. So the question that drives my research is, where do white dwarfs, magnetic white dwarfs, come from? That's because about 20% of white dwarfs are magnetic, and they span a huge range of magnetic fields, from a few tens of kilogauss to a gigagauss, so 5 orders of magnitude differences. And we still don't know why some white dwarfs are magnetic and where this huge diversity comes from. Of course, there's a lot of theories. They might come from single star evolution, or the magnetism can derive from interactions. And we expect at least one type of white dwarfs, the white dwarfs that come from mergers, so the merger of 2 white dwarfs, to be highly magnetized, because we expect very strong dynamos to arise during the actual double white dwarf mergers. And so I'm finally, so right now I'm wrong way. Okay, right now I'm focusing on trying to find the white dwarfs that are the product of mergers. And so on one hand, they are highly magnetized, and highly magnetized white dwarfs have homogeneous surface emission. So it might have bright spots or temperature gradients on their surface. And on top of that, we expect them to be rapidly rotating because of the conservation of the orbital angular momentum, right? Some of their orbital angular momentum will end up in the final merger product. And so we expect them to rotate much faster than normal white dwarfs. Normal white dwarfs rotate with periods from a few hours to a few days, while we expect mergers to rotate with the periods of order of minutes to hours. And so if you have something that is homogeneous and rotating, then you expect them to be photometrically variable. So the luminosity to go up and down with rotation period. And that's how ZTF comes in hand, because ZTF is these synoptic surveys and the optical that look at the entire northern sky every 2 nights. And so we have many, many, many images, hundreds of epochs of each source. And so we can look for periods and for periodic variability. And this is exactly what we're doing. We are looking in Gaia to identify interesting white dwarfs, and we follow them up with ZTF to see if they're periodic. And then we see this is a periodic light curve, but we want to make sure that it's a real period. And so we follow them up with CHIMERA, which is a fast photometer, fast imager on the Hale telescope. And you can see that you can get much better light curves. And of course, with Keck, to figure out if the white dwarfs are actually magnetic. Because from a spectrum, we can see, for example, the normal Barman lines that you see in white dwarfs. If the white dwarf is magnetic, you won't see only one Barman line for H alpha, but you'll see 3 because they're Zeeman splitted. And for very high magnetic field, you won't see them in where the usual H alpha stays, but they get shuffled around. And you'll find them in strange position that depend on the magnetic fields. And so this was the very first object that we looked at because it really stood out. It had a period of 7 minutes, extremely small for a white dwarf. And also it was one of the bluest objects in Gaia. You can see the Gaia SMB here. It was really, really, really blue. And for a white dwarf, being that blue means that it's very, very massive. And so we followed them up with LRIS and with UV photometry, and we actually found out it was extremely magnetic, 800 megagauss, one of the most magnetized white dwarf known. And then also that it was extremely small. Usually white dwarfs are the size of the Earth, normal white dwarfs. This one was the size of the moon, as you can see from this picture, so about 2,000 kilometers in radius. And since white dwarfs are more massive, when they're smaller, this is the smallest white dwarf known. It's so small and dense that in the core we have electron capture on sodium going on, similar to what happened, when neutron stars get formed. So this was a very interesting object, and it's kind of the poster child for a merger remnant because it's so massive, so rapidly rotating, and such huge magnetic field. And so this was really just the first one that we looked at. We then kept going, and we are still doing research, and we found a huge variety of objects that I'm now putting together. And we found highly magnetized white dwarfs. Here you can see what I was talking about is H-alpha splitted in multiple components. And so where they land on the spectrum changes depending on the magnetic field, and this is how I'm identifying the fields. So we're finding high fields, low fields, and also different compositions of white dwarfs. So it's not only hydrogen, they can have carbon, they can have helium, and then we're finding some very strange objects that I'm still trying to figure out what they are. And so right now I have a sample of about 50 candidates, and they're all very massive because that's where I was focusing on. We expect a large fraction of massive white dwarfs to be merger remnants, and so that's what I was focusing first. But I'm finding a huge range of magnetic fields, and most of them are with periods below half an hour. So this is really a very good sample of very high confidence merger remnants. And so again, I'm still putting this together, but once I have this sample, we can do a lot of things with it. We can study the properties of merger remnants. What are their distribution in masses, ages, and periods? How many are there? So we can kind of try to constrain the rate of merger remnants in the galaxy, and also from that maybe infer the contribution of mergers to the type 1a supernova. And then, of course, as I was starting at the beginning, trying to understand magnetic fields in white dwarfs. So this is still work in progress. Well, yeah, I think I sent you another slide, but it doesn't matter. One of the slides that I had here that I forgot to add is just to show that Keck has been fundamental in this work, because only with a 10-meter telescope, I can see these very shallow lines. And on top of that, only with Keck, I can look at phase resolved. So because these objects are rotating with periods of 10 minutes, maybe 5 minutes, some of them. And so to see how the spectrum changes with phase, I need to take 30 seconds exposures on objects that are maybe like 19 magnitude or something like that. So Keck is really, really important in this kind of research. And then there's another object that I found among my samples. And I think this is actually a new class of white dwarf. Please do not tweet, take pictures, etc., because this is still in review. But I found this object that is a white dwarf, pretty massive, around 1.2 solar masses. And you can see here the light curve. This is actually with hypercam, and it's pretty sinusoidal, 15 minutes. And this is the spectrum, the phase average spectrum. And in red are the helium lines, and in blue, I don't know if it's easy to see, but you can see the Balmer lines over there. So this is a helium hydrogen atmosphere white dwarf. But then when you go and look at the phase result, you see another picture. If you actually focus on the Balmer line, for example, this is H beta. These are different rotation phases of the 15 minutes. At phase 1, you can see all the Balmer lines are there. And at phase 0.5, the Balmer lines are gone. While if you look at the helium lines, like this one, for example, at phase 0.5, they're there. And if you go back to phase 1, they're gone. So this is a double-phased white dwarf with helium on one side and hydrogen on the other side. And so as it rotates, you can see the two phases. And it's really like a complete separation of the two elements, which I think it's one of a very exotic and fun object. We have some ideas of why this white dwarf is behaving like this. Well, we call it Janus because Janus is the Roman god of two phases, which is also the Roman god of transition. And so this might actually be a transitioning white dwarf, because we know that there is a range of temperatures between 30,000 and 50,000 degrees, when there's very, very few helium-dominated white dwarfs. And the reason why we think that's the case is because even if you have a tiny, tiny amount of hydrogen, it can float and cover the entire surface. So in those temperatures where the hydrogen floats up and it covers the entire surface of the white dwarf. But if the hydrogen is not that much, when you hit 30,000 degrees temperature, the convection in the helium layer right underneath the hydrogen can break into the hydrogen layer and dilute it. And so that's why below 30,000 degrees, we can see helium white dwarfs. And maybe this is white dwarf is actually transitioning outside of this gap, which is called DB gap. So this could be the first white dwarf that we see that is transitioning. Another possibility is that it has a hydrogen ocean. So if you have a magnetic field that is stronger on one side, you can create a sort of a pool. So the magnetic pressure is higher on that side and lower on the other side. And so the gas pressure is the other way around. And so the hydrogen can diffuse into the pool and create the hydrogen ocean on one side. Of course, we have to find more of these objects to really understand what's the reason for this behavior. And I think I found already another one. But yes, for this, as you could see this from the spectrum, this is another case in which Keck is absolutely necessary. That was like 3 hours of Keck just to get that phase resolved spectra. So I'm going to stop here and take questions. Thank you very much.
Awesome. Thank you, Ilaria. There aren't any questions on Slack, so are there questions in the room?
I've got a question up front from Adam.
Favorite one, Ilaria. I'm sorry if I missed it, but how are you getting the radii? Is it from the rotation period and the broadening on broadening?
Yeah, I didn't say that. So the question is, yes.
Can you repeat that one? That one was a little soft.
Yes, the question is, where do I get the radii? I do not get them from the spectra. Also because when the white dwarfs are magnetic, the lines, I cannot get the log G from the line, I cannot get the temperature from the line. So the way I'm getting the temperature is from the radii is from the SED. So often I follow them up in the UV to constrain the temperature better, and I have a very good distance from Gaia. That's how I get the radii.
And then Lynn has a question.
Similarly, is the magnetic field, is that just lambda squared or are there other parameters?
What do you mean how
Measure it? How you measure it? Is it just the lambda squared splitting?
So yeah, I can show it. I can show. Let me go back. So here is how I'm measuring. Okay, so maybe can I move this?
You can minimize it. Oh yeah.
Yes. Okay. So for low magnetic fields, as you can see, the splitting, how far away are the three lines depend on B squared. But for higher fields, as you can see, so these are down here at 1 megagauss, they are just a splitting. But if you get to higher and higher magnetic fields, the location of the transition is no more only 3 for each. So this is all H alpha. You get many more components. And they start shifting number in different position, and then the way you identify is really, for example, this is 105 megagauss, and this is, you see, I just look at the spaghetti plot, and you can see where the lines are, and you can identify the magnetic field by making sure that you get a line at all of the transitions. So this is a very good one because I have ones that are way less obvious. This one has a whole of the transition plus some forbidden ones, but the other times is way harder.
Oh, question in the back from now.
No, how do you place the final?
That's a good question. So, Janus,
Can you repeat these?
right. How can I say that Janus is not a binary? So actually, that's true. A lot of DAB white dwarfs turn out afterwards to be binaries. In the case of Janus, I'm really sure it's not, for different reasons. One is at 15 minutes periods, you would see very large Doppler shifts, which we don't see. Also, to explain the fact that you see only hydrogen and only helium, you would have to have an eclipsing binary. But if you remember, the light curve is just a sinusoid. So we are not seeing an eclipsing binary there. It's really just the white dwarf that is rotating.
All right, and we're out of time for questions.
Thank you.